How's it, China Beans? Let's jump into paper 2. Okay, so we've got daily sales of a tuck shop, and it's been given in a histogram, and we need to use that to fill in this table. So firstly, we're going to go to our 400 to 500 range, which is this bar over here, and we read off the y-axis. 1 above 10 will give us 11. So a little 11 will slot in here. And then to get the cumulative frequency, I'm going to take that 4 and add it with the 11, and I get 15 over here. And we're going to repeat that process. So let's read off all the y values. 5 to 600 will have a y value of 22. And then 6 to 700 has a y value of 15, 14, 13. So we can chuck a little 13 here. Okay, let's speed this up a little bit. We are going to get 7 there and 3 over there. 15 plus 22 will give you 37. 37 plus 13 will give you 50. 50 plus 7, 57. And then we get 60. And we've officially filled in the table. And your 2 marks come from the correct frequencies and the correct cumulative frequencies. In question 1.2, we need to draw a cumulative frequency curve, otherwise known as an Ogive, and we need to do it on the answer sheet that they provided. So you've got to get your points before you draw this. So your first point is always this beginning number over here and 0. So my first point is 300 and 0. Then what we do is we take our upper class interval or our upper class boundary, and we pair it up with the cumulative frequency as the y value. So this is your x coordinate, and this is your y coordinate that you get the coordinate 404 from. In a similar fashion, we're going to keep doing that down the table. So we're going to get 515 as our next point that we're going to plot, and speeding this process up a little bit, these are officially all the points we are going to plot. So let's quickly put them on our Cartesian plane. 300 and 0 will be precisely over there. And then we've got 404, 404. This goes up in ones because it's divisions of 10. So it's like 1, 2, 3, 4, so on and so forth. And let's speed that process up. And then we just draw a curve through all our points. And that is our cumulative frequency curve, otherwise known as an Ogive. And your 3 marks are earned from the correct starting point of 300 and 0, plotting the points correctly as well as the shape of your Ogive. In question 1.3, we need to use our Ogive to determine the estimated median for the daily sales. So what we need to do is actually find the position of the median, and we're going to do that by saying a half times our biggest frequency or our cumulative frequency. Because if there's 60 days in total, 30 days is like the halfway point. And that's exactly the answer over here. Half of 60 is 30. So what we're going to do is we're going to find 30 on the y-axis here, the cumulative frequency axis. And then once we found 30, we're going to go across to our Ogive, and then we go down and we find the estimated median. So you can see here these divisions are like 20 bucks. So that's like 500, 520, 540, 560. So I kind of landed by 580 Rand. And this is our estimated median. So we simply just read it off the Ogive like so. And your 2 marks just come from the answer only, and you've got a bit of wiggle room here, so they accept any answer in between 560 to 600 Rand. In question 1.4, the tuck shop must make 475 Rand to break even for the day. How many days did the tuck shop make a profit? So we're going to grab this 475 and we're going to find it on our daily sales axis. It's going to be roughly somewhere here. And then we're going to follow that up to our Ogive, and we're going to follow it across to the y-axis. And now all the days under this will be the days I made a loss. and all the days above this is where I made a profit. Because on these days, I'm making more than 475, and on the last days, I'm making less than 475. So, to calculate how many days we had a profit, we're simply just going to say 60 minus 10 to give us our 50 days. And you purely get your marks from the answer here. 2 marks purely for the answer. In question 1.5, the tuck shop made 725 Rand in sales, and we didn't even know, does this lie within the top 25% of sales from the previous 2 months? So we actually need to know where the top 25% is to determine whether the 725 Rand falls within it. And 25% of something is a quarter of something, so we're going to have to use quartiles to solve this. So if I want the top 25%, I want to go for the upper quartile. So I want Q3. And to get Q3, I need to know the position of Q3. And to get the position, you just take 3/4, multiply it by 60, which is the highest cumulative frequency that you can find on your Ogive. Pop it into your calculator, and it returns you 45. Then you come to your Ogive, and on the y-axis, you find your maximum and Q3, and then you go across, and it's going to tell you where the top 25% is when you go down over here. So if I go down over here, I go to roughly about 900 over there, and I go to roughly about 650 over there. So now I know what Q3 is. Q3 is 650. And now I'm going to check out the 725 Rand. Does it fall within the top 25%? It most definitely does. It's bigger than 650 and smaller than 900 at the same time. So yes, it definitely does lie within the top 25% of sales. And you will get 1 mark for the value of Q3 and 1 mark for your conclusion. In question 2.1, we've been given 5 data values as follows. And if the mean is 15, we need to show that k equals 11. So if they say show that k equals 11, you cannot use that 11. You must show where that 11 came from. So we are going to be using our mean formula to do that. So the mean is equal to, and then I add together all my data values on top. So I take all these data values and I simply add them together, and then I divide by the number of data values. They told us that there's 5 data values. And then to work this out, I start off by multiplying these 2 numbers. 15 times 5 will give me 75, and then that's equal to, now I'm going to do all the k's on top. So 2k plus 1k plus another 1k plus 1k plus 2k gives me the 7k over here, and 1 plus 2 minus 3 minus 2 will give me this minus 2 over here. There are no more fractions left because I kind of cross multiplied that 5 up there to get this 75. So this 5 disappears, it kind of morphs into that 75. And now we just need to solve for k. So we're just going to grab that -2, move it over, it becomes plus 2, 75 plus 2 is 77, and then we just divide by 7, and we get k to be 11. And our 3 marks come from dividing by 5, getting that 7k minus 2, as well as your manipulation to solve for k. In question 2.2, we are instructed to calculate the standard deviation, rounded off to 1 decimal place. And we always use our calculator to find standard deviation. So here's our calculator steps to actually calculate standard deviation. But I'm going to need to enter in my data values, and I can't enter k's into my calculator. So from the previous question, they told us that k was 11. So I'm going to fill that 11 into all the k's I see here. Let's start with the first one. So 2k, 2 times 11 will give me my first data value to be 22. My second data value is just k plus 1. So 11 plus 1 will give me 12. Speeding that process up, let's just quickly work out all of them. Okay, now we're going to bust out our calculator bot. Okay, and then let's start going through the steps. So mode 3, 1. Now I enter in all my data values. So I press 22 equals 12 equals. And speeding that process up, I've got 5 data values. The last one is 20. Now it may seem scary, but we're going to press AC. And then we press Shift and 1. Then we go to number 4, var. And then we want the standard deviation. So we're going to choose 3. And then we press equals. And then we want that to 1 decimal place. So it's just going to be 5.2. And there's our standard deviation, just 5.2. And your 2 marks are awarded purely for the answer. In question 2.3, t units are subtracted from each data value in the set. And without further calculation, I need to explain how the mean and standard deviation are affected. So let's grab our data set. We're firstly going to talk about the mean. So what's happening is I'm minusing t sort of units from each data value. And what really helps me wrap my head around this is just choosing a random number. So let's say t was 2. So I just minus 2 from each data entry. And it gives me a new data set. And I can see with this new data set, all these data values are lower. So the average is going to get lower. If I have lower data values, I'm going to have a lower average. And we know that it's going to be lower by a very specific amount. Each one is lower by t units. And that sorts out the mean. Okay. Now to talk about the standard deviation, I've got to talk about the spread of the data. So I'm going to come look at the spread here. You can see the difference between 22 and 12 is 10. The difference between 12 and 13 is 1. The difference between 13 and 8 is 5. So that tells you about the spread. Now our new data set has the exact same spread as the previous one, which leads me to conclude that if they have the same spread, it's the same standard deviation. The standard deviation will remain the same. And your 2 marks are simply awarded from each conclusion regarding the mean as well as the standard deviation. In question 3, we start off with our analytical geometry. We've been given the following diagram with 3 coordinates, and we need to determine the gradient of the line MQ. So in grade 11, there are 5 ways to determine gradient, but if I have 2 points on my line, then I can simply just use my gradient formula. And it really does not matter which order you put the points in. I like to put the top point in first. So I'm going to put -2 and 0 into y2 and x2's place. And just remember the y value goes on top. So that 0 will go on top here. And the -2 will get filled in at the bottom because it's an x value. Now let's chuck our pink point in. I'm going to put the -2 on top because it's a y value. And the 4 will go to the bottom because it's an x value. Now ain't nobody got time for that, bruh. That's going straight in the calculator. Okay, so we're going to slap that in and we get -1/3 as our gradient. And at the same time, I like to put that on my sketch. It really helps you with later questions. And we can see from left to right, this graph is going downhill. So a negative gradient makes perfect sense. In question 3.2, we need to find the equation of the line MP in the form y equals mx plus c. So I'm going to represent MP with this orange over here. And let's analyze what y equals mx plus c is all about. So the letter M is representative of your gradient, and the letter C is representative of your y-intercept. And if we go to that orange line, oh my gosh, look at that. There's the y-intercept. So let's pop it in. Simply just by changing this C to a 6, like this. Okay, now we need to get M. So how I can get M is I can use the gradient formula between these 2 points, or I can simply just substitute a point in. I'm going to go the second route and substitute a point in. And to choose the point to sub in is a little bit tricky. We've kind of already subbed this in by placing the 6 there, so we have to choose the letter or the coordinate M to sub in. And then when I sub in, just remember the first one goes into x's place and the second number goes into y's place. So let's go ahead, make that switch. And now all that's left to do is solve for m. So what I'm going to do is I'm going to take the 6 over to the other side. It becomes minus 6, and minus 2 times m will give me minus 2m. I divide both sides by negative 2, and that will give me a gradient of positive 3. It makes so much sense because this is going uphill. So now we're going to put that 3 back in here to finalize the equation for MP. So let's chuck him back in quick, and we get y equals 3x plus 6 for the equation of MP. And your 3 marks will be awarded for substituting in the correct C value, doing the correct substitution, as well as the correct final answer. And for question 3.1, you get 1 mark for your substitution and 1 mark for your final answer. A good tip for analytical geometry is all your previous answers, put them on your sketch. It really helps, and make your gradient stand out a little bit. I know the gradient of this line is 3 just by looking at the number in front of x. And now we need to determine the coordinates of r. R is situated all the way on the left over here. And what I'm noticing about R is that it's the end point for a line that we have the midpoint for. So we've got the end point and the midpoint, and we need the other end point. And also I'm missing 2 variables. I'm missing an x and a y, and that's a kind of giveaway that I have to use the midpoint formula. Now when I'm getting an endpoint, I split the midpoint formula up into 2 separate formulas. One that deals with the x values exclusively, and another one that just deals with the y values. So we're going to use the bottom formula, not the original midpoint formula that's on the formula sheet, the split up version which is not on the formula sheet. And now we're just going to simply fill everything in and solve for the missing variable. So the x in the middle, or the midpoint, is minus 2. So I'm going to change this to minus 2. And then x1 and x2 are the x values at the end. So that's going to be 4 plus, and I'm just going to name this xr, the x coordinate that belongs to coordinate r. So let's go ahead and change those top 2. Okay, and then while we're here, let's do the same thing for the y values. The y value in the middle is 0. So I'll replace this with a 0. And y1 and y2 are the y values at the end. So it's this minus 2 over here and the yr. So it's just going to be minus 2 plus yr. And now that everything's filled in, we just need to solve for x and y. So over here I'm going to cross multiply that 2 up there, and it will give me negative 4. And then the top remains unchanged. So this will just equal to 4 plus xr. Now I'm going to move that 4 over. It becomes negative 4, and I get negative 8 as the x value for r. So now we know half of the coordinates of r. It's negative 8 and something. So let's go ahead, repeat that process for the y's. So we're going to multiply that 2 up with the 0. 0 times 2 is just 0. And the top will remain unchanged. You just have minus 2 plus yr. I'm going to grab this negative 2, move it over there, and it becomes plus 2 when I move it over the equal sign. So now we know the y value for r, and our job is officially done. And having a look at the marks, substitution earns you your first mark, and each respective x and y value gets you the second and third mark. And just remember to transpose your answers on the sketch, put them on the sketch. Next up, we need to calculate the length of PQ in simplified third form. So length is an acronym for distance. So we shall use our distance formula to calculate that. It's pretty stock standard. We're just going to pop our 2 points into the distance formula to get the length. And we've got to put any coordinates, it doesn't matter which one I start with, into the purple guy's place. I like to start with the top one. So I'm going to put this 6 into y2's place and this 0 into x2's place. And then the other coordinate slots into x1 and y1. So I'm going to put -2 into y1's place, and I'm going to put 4 into x1's place. And just remember, if you have negatives, to wrap them in brackets. Okay, and then we're just going to slot that in the calculator. That is a calculator problem, not ours. So Uncle Calculator tunes us, it's 4 root 5, and we've got to leave our answer in simplified surd form, so we just leave it like that. The square root is the surd that they are referring to. So PQ has a length of 4 root 5 units. And just in case you're curious, that's about 8,94. And your 2 marks will come from your subs and your answer. In question 3.5, we've been told that RPQT is a parallelogram, and the coordinates of T are somewhere in the third quadrant. So let's just go through which quadrants are which quickly. So this over here is quadrant 1, and in the top left corner is quadrant 2, and the bottom left hand corner is quadrant 3, and lastly in the bottom right hand corner we have quadrant 4. So the fourth point of our parallelogram will lie somewhere in quadrant 3 for this question, as they told us here. So it's going to be like somewhere down there, and the parallelogram will look something to this effect. And the coordinates of T will lie somewhere down here. Now we're going to analyze our gradients to pull this off, like so. So whatever I do to get from this point to this point, so however much I go down and across is the same as what I'm going to do to go from this point to this point. So I'm going to go down the same length and across the same length to get to T. So let's see how much we go down. We're going from 6 to -2, which tells me I'm going down 8 units. I have to go down 6 to get to the x-axis, and then I have to go down another 2 to get down to -2. Or you can say top minus bottom. 6 minus -2 will give you +8. So that means I'm going to go down 8 this side. Now let's analyze how much we go across. To go from 0 to 4 must be 4 units. So on this other side, I'm also going to go across 4 units. Okay, now with this we can get T. And to get the x value of T, we exclusively look at the x value and the horizontal movement. So I'm going from -8, 4 units that way. It will take me to -4 because I'm adding 4. And then if I go down 8 units, I only look at the y value. So 2 minus 8 will give me -6. And now we officially have T to be -4 and -6. And you'll earn 1 mark from your x value and 1 mark from your y value. In question 3.6, we need to explain why RPQT is a rhombus. So RPQT, they told us in the previous question that it's a parallelogram. So the deciding factor that changes a parallelogram into a rhombus is if the diagonals are perpendicular, and they are. So that's exactly our reason. So if you have a parallelogram and you see a 90-degree here, that automatically makes it a rhombus when the diagonals of a parallelogram are perpendicular, because that is the crucial difference between them. We can also prove that adjacent sides are equal, but that's a very long way around, especially for 2 marks. And you'll simply be awarded for one mark for the diags of a parallelogram. That word has to be there. You cannot say quadrilateral. And the second mark comes from saying are perpendicular. In question 4, we continue with analytical geometry, and we've been given the following diagram. And we've been given the equation of AC. It's quite a weird one, but let's transpose that information onto our sketch and let's get busy. So I need to determine the coordinates of C. So if I look at the green line, C is a very special point. It's the y-intercept, my China bean. Okay, and what do we know about the y-intercept? We know that the x value is 0, and if we want to solve for it, we let x equal 0 and then solve for y. So we're going to do exactly that. We're going to grab the equation of AC, replace this x with a cheeky little 0, and then we solve for y. Now to get y on its own, I need to do the following steps. I'm going to move this minus 5p over to the other side. And py minus 0 is just py. It's like saying 7 minus 0 is just 7. So I get py equals 5p. And now the end mission, I need y on its own. So I need to get rid of the p's. And I'm going to do that by dividing both sides by p's. The p's on the left hand side will cancel with one another. These p's will also cancel with one another, leaving us with a y value of 5. And now we know the coordinates of C will be 0 and 5. So we just need to state that just by writing it somewhere in our answer like this, and then we've officially wrapped up the question. And our 3 marks come from making x0 our manipulation as well as the final answer. In question 4.2, they tell us that the gradient of AC is half, and with that we need to show that P equals 2. So I'm not allowed to use this P equals 2. I've got to show where it came from. So my first instinct was basically to sub this point into that line to get P. But that was unsuccessful because it just gave me 5P equals 5P. So I've got to find another way around. So I'm focusing my attention to this point here. I know a little something about that point there. I know its y coordinate is 0 because it's an x-intercept. And now if I have the gradient of this line, I can get this missing point by just utilizing my gradient formula. If I have 4 of these guys and I need a 5th, it is possible to solve for the 5th. So the gradient, I'm going to change it to a half. And then for my first coordinate, as you know, I like using the top one. So I'm just going to pop that 5 into y's place and that's 0 into x's place. And now let's pop in the other coordinate on our line. It's this purple one over here. So the 0 will go on top and the x value for coordinate A will go at the bottom. And now I'm just going to solve for x over here. So at the top, 5 minus 0 will just give me 5. And 0 minus xa is just minus xa. It's like 0 minus 7 is minus 7. And now I just need to cross multiply to get rid of the fraction. So minus xa times 1 is minus xa. And 2 times 5 will give me 10. And then this negative, I transfer it to the other side. I basically divide both sides by negative to get rid of it. And now we know that the coordinates of A is minus 10 and 0. Now we can kind of return to our original mission and take this point and sub it into that equation and solve for P. So we're going to grab that equation and we're going to change x to minus 10 wrapped in a bracket because there's a minus in front. And we're going to change this y to a 0. P times 0 is just 0. Minus 10 is positive 10. And the minus 5p can stay where it is. Then I'm going to yoink that over to the other side. And it becomes positive 5p. Divide both sides by 2. And 17 years later, we have p equals 2. So now, they didn't quite ask you to get p. What they're also asking you is to complete the equation of AC. So what I like to do is this P, I'm going to replace it with my answer like this. And then I reorganize it. So 5 times 2 is 10. And then I move that minus 10 over. And I move that minus x over. Divide everything by 2 so that the standard form of my line appears. And I can read off the gradient of my line, as well as the y-intercept of my line. Okay, and the slag means I only award 2 marks, one for A, one for P. In question 4.3, we need to calculate the coordinates of B. So let's have a look at B. We're missing x and y, so I'm missing 2 variables. So I'm going to need 2 equations to solve for those 2 missing variables. So I've got the first equation here. From the previous question, we know the equation of this line is y equals a half x plus 5. But I don't have the equation of the blue line. I need the 2 lines that touch B, that intersect over there, so that I can apply the following rule. To get the points of intersection, I can make the two graphs equal to one another and solve for x. But I don't have the equation of the blue graph, so we're going to have to go on a side mission to get it. And we're going to do it with our classic y equals mx plus c. And then I see a 90-degree angle over there, which will enable me to calculate the gradient of the blue line using my perpendicular lines formula. So let's go get the gradient quickly. So I'm going to put in the gradients of the green line here, because that's the one that's perpendicular to the blue line. The gradient of the green line is this half over here. So let's chuck him in. And then minus 1 divided by half will give you minus 2. And the honorable calculator agrees with me, you see? Yes. And just another thing, you can change like M2 to MBD. You can state the line that you're getting the gradient for. Okay, we're going to take that gradient, slap it straight into y equals mx plus c, but... And now I'm going to start hunting for that y-intercept. Do I have the y-intercept of the blue line? Hey, how's it? But minus 10, yes. So we can replace c with minus 10. And now we officially have the equation of the blue line. And now that we have the equation of the blue line, we can jump back into our original mission from earlier, where we're going to get the points of intersection and make the equations of the two graphs equal. So I simply just do that by grabbing the equation of the green graph, half x plus 5, equals the equation of the blue graph, minus 2x minus 10, just like this. We make them equal and we solve for x. So we're going to get all the x's to one side and all the numbers to the other side of the equal sign, because it is a linear equation. So when I move this 2x over to that side, or the minus 2x, it becomes positive 2x because we're moving it over the equal sign. So we're going to get a half x plus 2x. I'm going to ask my calculator to help me out there. And you just type it in without the x's. So you can see there, half plus 2 gives me 5 over 2. So on this side of the equation, I'll get 5 over 2x. And if I take this 5 over, it becomes negative 5. Minus 10 minus 5 will give me minus 15. And then I divide both sides by the number in front of x. Just make sure when you type it in on the calculator, you say minus 15 divided by a fraction like this. And then that's going to give us negative 6 for the x value. So we're almost there. We now know that b has an x value of negative 6. To get the y value, I simply substitute that negative 6 into the equation of either graph, because it lies on both graphs. I think this graph looks easier because there's no fractions, so I'm going to sub it into the blue graph. And all that entails is changing this x to a negative 6, just like this. Okay, then we're going to slide that into our calculator, and it returns us y equals 2. So now we know that the full coordinates of b are negative 6 and 2, and that makes so much sense. B is in between an x value of 0 and negative 10, so negative 6 fits in that criteria perfectly, and the y value will have to be in between 0 and 5, and 2 fits that criteria perfectly. So we're in the right regions and things are looking good. In this question, you get 4 marks from the following steps: the equation of BD, the substitution, the x and the y value, and the 5th mark will come from this step that we did previously, where we put p in here to get the equation of our green line. In question 4.4, we need to determine the size of alpha. Alpha is an angle that's down here. Anytime I want to get angles in analytical geometry, I need to use my angle of inclination formula, which is m equals tan theta, m representative of the gradient, and theta is representative of your angle of inclination. So if I have an increasing line, it's just from, you basically go a little bit right of your line, and then you go anti-clockwise till you touch your line. So if I demonstrate it with this line, I'll go a little bit right, go anti-clockwise till I touch my line. So alpha is in fact the angle of inclination for the green line. So we can just put the gradient of the green line into this formula straight away, and solve for the angle of inclination, which is alpha. So let's make those changes. So we're going to change the gradient to a half, and we're going to change the angle of inclination to alpha, because they've named it alpha. And then, to solve this, we can ignore the special rule. My gradient is not negative, so we do not have to add 180. I'm going to break the tan up from the angle and move the tan over to the other side, and it becomes shift tan. And then that alpha equals, I'm just going to move it to this side to make my life more convenient. And then we just pump that into our calculator, bro. Okay, so when we pump that in, we've got to round it off to 2 decimal places. So if it's 5 or more, you let it soar. If it's 4 or less, you let it rest, my bro. So this 5 will round that 6 up, and we get 26.57 degrees for alpha. Tasty, but. And your 2 marks will be awarded for the correct substitution as well as the answer. In question 4.5, hence means use your previous answer. We calculated this angle in the previous answer to help us prove that ABOD is a cyclic quad. Yes, how did Euclidean sneak its way into analytical geometry? Okay, let's go through the 3 ways I can prove a cyclic quad. So I can firstly prove that the opposite angles add up to 180. I can prove that the interior angle equals the opposite exterior angle of a quadrilateral. Or I can prove that I have equal angles in a bow tie and that it's converse angles in the same seg. If we have a quick look at our diagram, I am seeing a bow tie if I draw this imaginary circle. Let me demonstrate. So I've drawn the imaginary circle that they're asking for in grey. And then the bow tie will be this red guy here. Let me delete those 2 lines so you can see the bow tie even better. And I knew to use the bow tie because of this word, hence I want to incorporate my previous answer. So now I want to solve for beta, prove that these angles are the same, and then I can leap to my conclusion that this grey circle is a cyclic quad. So let's see how we're going to do that. We're going to need to get beta, so we're going to make use of our angle of inclination formula. So let's have a look at our formula. We've seen it before, gradient equals tan theta. So if I look at the blue line, my angle of inclination, I find the x-intercept, go a little bit right, and then anti-clockwise. So I find my x-intercept there, a little bit right, and if I go anti-clockwise, that will be the angle of inclination for the blue line. So let's go ahead and get it quickly. We're going to use that to get beta later. So the gradient of the blue line is -2. So we're going to put that into the gradient place. And then I'll just leave this as a theta. It's representing this arbitrary angle here. There's no other theta, so there's no name clashes. Okay, I'm going to take the tan over. It becomes shift tan. And we are also going to see this small rule come into effect. Do you see how my gradient is negative? So in this line here, I've got to add 180 degrees. So that gives me the true angle of inclination. Okay, let's opgepomp that into the calculator. So Dr. Calculator returns us 116.57 degrees. So now we know that this angle is 116.57 degrees. Now, we're going to use that to get beta with the following triangle. So with this orange triangle, this corner of the orange triangle is 90 degrees. Every little corner on the Cartesian plane is 90 degrees. And then this angle over here, if I just had to extend this line of the orange triangle, we can a bit more clearly see that this 116.57 is an exterior angle of this orange triangle. And basically, to get an exterior angle, you add together the 2 opposite interior angles. So 90 plus beta will equal this 116.57. So it stands to reason that beta will be equal to 116.57 minus 90. And if we just pop that into the calculator, we will get the exact same size as alpha, which is exactly what we were expecting, 26.57. Now we can see that bow tie, but check it out, bro. Check how those angles are equal, man. Yeah, bro. And then all that's left to do is we've got to state that alpha is equal to beta. And then we can make the conclusion that ABOD is a cyclic quad. And the reason is converse angles in the same seg. And in this question, beta gets you a mark, your reason gets you a mark, as well as the size of this obtuse exterior angle of triangle. And rounding out question 4 with question 4.6, we need to get the coordinates of the center of a circle which passes through D, B, and C. So your circle will pass through D, B, and C. And if I want the center of that circle, I'm going to have to utilize this 90 degrees. I've got to follow that 90 degrees back and back some more so that I actually know where the diameter is on the circle, because I am following the Euclidean Geometry theorem that states that if I have a 90 degree angle on the circumference of a circle, I can follow that back and it will take me to a diameter, converse angles in a semicircle. So now that we know this is the diameter, we can simply get the halfway point of that line, and that's the center of our circle. So we're going to use the midpoint formula, but... And let's decide what version we're going to use. I am getting the midpoint. I'm getting the points in the middle. I have the two end points. So I'll use the first easy version. Okay, let's chuck in our x values. x1 and x2 are just the x values at the end. Crispy 0 and 0. Okay, let's have a look at our y values next. Just simply add the y values together at the end. So it's 5 plus -10. And just don't forget to wrap negative numbers in brackets. And then we're going to slap these two separate calculations on our calculator. 0 plus 0 is just 0. 0 divided by anything is just 0. Okay, and if we chuck this into our calculator, it turns us -5/2. But alright, and now we are done. That is the center of the circle that they are referring to. And you're going to get a mark pop, one for x, one for y. In question 5, we start off with trigonometry, and they told us with the aid of a diagram, so that means we're going to have to do a sketch. And if we're going to do a sketch, we need to decide what quadrant we're going to be working in. So first things first, we need to grab this 3 sine beta equals 2 and get sine on its own so that I can assess whether sine is positive or negative. In this case, we can clearly see that sine is positive based upon looking at this fraction here. And then we're going to draw a little cast diagram, and sine is positive in the first and second quadrant according to your cast diagram. Then we come and have a look over here. Now this is very sneakily telling you that cos is negative. And cos is negative in quadrant 2 and quadrant 3 because it's positive here, so it has to be negative in those two. Now we set up a sketch in the second quadrant where this obtuse angle over here is our angle beta, and then this will adopt the place of our reference angle. And we come have a look over here, and according to Sokotoa, this must be the opposite, and this must be the hypotenuse. So we're going to fill it in on the sketch accordingly. The hypotenuse is opposite this 90 degree angle, it points at the hypotenuse. So we'll fill a 3 in there, and 2 opposite the reference angle. Now we're going to make use of Pythagoras to work out the missing side. And we start off that process by just calling the side x because it goes left and right. And then I'll say the hypotenuse squared, 3 squared equals this squared plus this squared. Okay, once that's out the way, 3 squared is 9, 2 squared is 4. And if I take that 4 over, it becomes -4. So 9 minus 4 will give me 5. And then to get rid of the square on x, we need to square root both sides. And then just don't forget the plus minus in front of the root when you do that step. Now we've got to choose the right one according to where it is on the Cartesian plane. This is the positive x-axis, this is the negative x-axis. So we're definitely going to have a negative x value. So we're going to choose negative root 5. And after all that set up, we're finally ready to answer this question. So the best place to start is you keep the structure of the question the same and you change cos to an empty bracket like so. And then we're going to go get cos beta using ka from the sketch and put it inside this empty bracket. So let's go ahead and do that. Cos is adjacent over hypotenuse. So adjacent to my reference angle is minus root 5 and the hypotenuse is 3. So we go ahead and slot that in here. Once that's out the way, I square the top and I square the bottom and I do not touch anything else. If I square root 5, it's just 5, and if I square 3, I get 9. And bear in mind, a negative times a negative is a positive, so this negative essentially disappears. Now we need to simplify. So we start that process off by putting this 3 over 1. We find the biggest number that can go into the top and the bottom. I can divide the top and the bottom by 3. So 9 divided by 3 will give me 3, and 3 divided by 3 will give me 1. And now I just do top times top and bottom times bottom to get my new fraction over here to be 5 over 3. And this whole time the minus 1 just chills on the outside, and now 5 over 3 minus 1. Convert that 1 into a fraction quickly, 3 over 3. 5 minus 3 will give me 2, so the final answer will be 2 over 3. And we have officially wrapped up this question. Quickly having a look at your 4 marks. Quadrant 2, the value from Pythag, substitution of cos beta, as well as your answer. In question 5.1.2, I so desperately want to reduce this guy, but I can't. I can only reduce it if I see these 3 things, 180 minus, 180 plus, 360 minus. So there's a simple solution to that problem. We just need to add 360, and then we're going to get back to a familiar territory. So minus 180 plus 360 gives me positive 180. And then I put the positive 180 first, and I put the minus beta second. And now we set up for that reduction. You see we have 180 minus. So in that quadrant, tan is negative because only sine is positive there. So we reduce this to negative tan beta. And now I'm going to replace tan beta with an empty bracket, keeping everything else about the structure the same. You see how the minus stays behind? Now tan beta, I'm going to use TOA and my sketch to fill it in. So tan is opposite over adjacent. It's all relative to the reference angle. So the opposite is 2 and the adjacent is minus root 5. So inside of this bracket, I put 2 over minus root 5. Negative and a negative cancel out to give me a positive, and I'm just left with 2 over root 5. And your 3 marks will be awarded for your reduction, substitution, and answer. In question 5.2, we've been given that t cos 15 equals 4. And we need to determine the following in terms of t without the use of a calculator, sine 15 and sine 75. So without the use of a calculator is a serious clue that you actually need to do a sketch. And if we fall back into our procedure with sketches, I want cos of 15 on its own. So I want to get rid of this t. And we're going to accomplish that by dividing both sides of the equation by t. And then they cancel on the left hand side over here. And I'm left with cos of 15 degrees equals 4 over t. And then we analyze this line like so. Because we're working with cos, that is the adjacent over the hypotenuse, so this top number is representative of the adjacent, bottom number represents hypotenuse. Now 15 degrees is in the first quadrant, so we're going to set up a sketch that is in the first quadrant. So just think of your bow tie when you go ahead and sketch this triangle. And then this 15 degrees is always the angle that is closest to the origin. So we just fill it in over there. Then I always like to work this angle out using interior angles of triangle. 180 minus 90 minus 15 will give me this angle to be 75. And hey, would you look at that? They're going to test it. That's why I always get it. And then we fill in our adjacent and hypotenuse. So adjacent to the 15 will go the 4. And our hypotenuse gets filled in as t because that's at the bottom over here. Now to get this missing side, we're going to use Pythagoras. And we'll start off by naming it y because it goes up and down. So to start off with Pythagoras, it's my hypotenuse squared equals. So my hypotenuse goes first, that's the t because it's across from the 90-degree angle. And then it equals to this side squared plus the side squared. Now that 4 squared, we are going to yoink it over to the other side. The whole goal is to get y on its own. So if I yoink it to the other side, it becomes minus 4 squared. 4 squared is 16. So I just square root both sides to get rid of this square on y. And we get y to be t squared minus 16 underneath a square root. And we just replace that y with the t squared minus 16 under the root. And now we're finally ready to answer the questions. So sine of 15, I'm going to use saw with the 15. So sine is opposite over hypotenuse. So if I go to the 15, opposite over hypotenuse. So it's the root over t, just like this. Okay, we're going to do the same thing for sine of 75. So if we have a look at sine of 75, this is now our reference angle. So opposite over hypotenuse, opposite the 75 is 4 and the hypotenuse is t. So this will just evaluate to 4 over t. And then we've officially wrapped up this question. Quickly having a look at your marks. 1 mark for isolating cos of 15. 2 marks, 1 for that square root and 1 for t. And then 2 marks for the answer only in this question. And rounding out question 5, we need 1 minus tan squared 15, and we need to give the answer as a single fraction. So how we cope with squares is we kind of like put them on the outside and we replace tan of 15 using TOA and our sketch. So let's go ahead and get tan of 15. Opposite over adjacent, I'm using 15. So opposite over adjacent, the root over 4. Now I give priority to the square, so how I get rid of it is I square the top and I square the bottom. If I square the top, it's going to cancel out with this square root over here, and if I square 4, that will give me 16. Now we need to focus on turning this into a single fraction as they instructed. We're going to do that by getting the LCD. So the LCD will be 16, so I need to change this 1 to 16 over 16. Now we're going to morph these guys into one big fraction. So I'm going to draw a big divide line with 16 at the bottom. And then I'm going to say 16 minus this guy in a bracket. Don't forget a bracket. You're subtracting the whole thing. So it's 16 minus t squared minus 16 in a bracket. Okay, we're going to distribute that negative into the bracket. So we're going to get a sign change happening over here. And then we just do our like terms. 16 plus 16 will give me 32. So I can change that at the top. And we'll just be left with 32 minus t squared over 16. And now we've adhered to the extra instructions. Our answer is a single fraction. So let's have a look where our 3 marks will come from. Substitution of tan 15 gets you the first mark. Squaring that bracket correctly gets you the second mark. And the correct multiplication for your LCD earns you the third mark. Question 5.3, we need to simplify this trigonometric expression to a single trig function. Okay, that 90 minus, if I analyze that, it's a co-function. So it changes to sine of alpha, using this little co-function over here that you need to know off by heart. This over here, I can't reduce that. So I need to add 360 to it twice. That will change it into sine of negative alpha plus 180. And then I simply swap the order. I put the 180 first, then I put the negative alpha second so that I can reduce in the next step. Now it's in the 180 minus quadrant. Tan of 225, we split the 225 into 180 plus 45. And then we reduce it in the 180 plus quadrant. Tan is positive. So that will get reduced to tan of 45 degrees. This sine of alpha can stay, it's simplified as far as possible. Sine of 180 plus alpha, 180 plus, it can be reduced straight away into negative sine alpha. Sine is negative there because the only positive one is tan. Okay, now we're going to analyze it one by one, exactly how we did in the first step. So this first sine alpha can stay. Sine of 180 minus alpha, we're going to reduce that guy. and we get sine of alpha, because in the 180 minus quadrant, sine is positive. Tan of 45 is 1. You should know your functions well enough for special angle triangles well enough to get that, instead of using your calculator. Positive times a negative will give me a negative over here, and then sine times sine will give me sine squared of alpha. Okay, now at the top I've got sine times sine, which will give me sine squared. And at the bottom I see an identity, 1 minus sine squared, that changes into cos squared of alpha. So we're using this identity at the bottom, which is a derivative of our Pythagorean identity. So let's go ahead and change that to a cos squared. And now I see another identity. Sine over cos gets changed into a tan. And it does work with squares. If these are squares, sine squared over cos squared can change into a tan squared of alpha. And now we've officially finished the question. We've simplified it to a single trig ratio. And your 5 marks are awarded for the following steps. In question 5.4, we have a trigonometric equation. So we've got to turn this thing into this thing. Useless. Okay, so what I'm seeing is this one has sine squared, but this one does not have sines. So I want to get rid of the sine squared, and we're going to do that using trig identities. And the relevant trig identity will be this guy. Sine squared theta is equivalent to 1 minus cos squared, because if you look at your Pythagorean identity and move that cos squared over, it becomes minus cos squared and you get this identity. So now we're going to make the replacement. So we're going to keep the structure exactly the same. We're going to put some open brackets where sine squared used to be. And then inside of that, we chuck the 1 minus cos squared, but the identity. Okay, now we've got a set of brackets that we need to get rid of. So this 2 over here, we simply just going to distribute him into the 1 and into the minus cos squared theta. After I do that, 2 times 1 is just 2, and 2 times minus cos squared is minus 2 cos squared theta. Now what we have over here is a trinomial, because I've got cos squared, I've got cos, and I've got some numbers floating around. So if I have a trinomial, I want to reorganize it so it's in the right order to set me up for factorization. So this minus 2 cos squared theta, I'm going to take it over to the other side of the equation, and I want that guy first. So we just go ahead and place him first. Now this minus cos theta, I want that in the middle. And it did not move over the equal sign, so it stays negative. And then this 1 I'm going to move to the end. And this 2 over here, I'm going to take it over, and it becomes minus 2. And 1 minus 2 is negative 1. And now we have the standard form of our trinomial, and we can start the process of factorization. So we're going to factorize it just like we do in algebra. I'm going to change the cos's to x's just to make my life a little bit easier. And now we're going to set up the tennis court method because there's a number in front of x squared. So we're going to start that off by writing the factors of 2 underneath each other over there. And then we write the factors of 1 underneath each other over here. And luckily 1 is a prime number. Well, it's not a prime number, but it's only got 1 and 1 as a factor. Then we're going to go across the court like we're serving in tennis, hence the tennis court method. And we just multiply going across. So 1 times 1 is 1, 2 times 2 is 2. Now I've got to add or subtract these numbers to get this negative 1 in the middle. So let's see how we can do that. So I think I can get it done just by saying minus 2 plus 1. And then once we have our signs, we transfer that sign back here. We transfer this sign back here. Chuck a little x here, chuck a little x here. And now we officially have our 2 brackets. So the first bracket is 2x plus 1. But bear in mind I'm not working with x's, I'm working with cos's. So I just change this x to a cos theta. So it's 2 cos theta plus 1. The second bracket will be x minus 1. But we replace x with a cos theta. And now we've officially changed this general equation into this general equation. Your 2 marks. Sleg, bruh. Making use of your identity gets you the first mark, and your standard form gets you the second mark. In 5.4.2, they said hence, which means we need to use our previous answer to help us. We need to determine the general solution of this. This is our previous answer, so let's grab it and use it. So we firstly grab it, and then we need to use the zero factor theorem to solve it. So we're going to make our first factor equal 0, and our second factor equal 0, with the word or separating them. I'm just going to start off with the first factor, so I'll grab the contents of that bracket, make it equal to 0. And the first step is to get cos theta on its own. So I'm going to quickly move that 1 over, it becomes -1. Divide both sides by 2, and I get cos theta equals -1/2. And then I'll start sniffing around this line. I'm like, how's it but? I can see our cos is negative. So we set up a little cast diagram to decide what quadrants we're working in. Cos is positive here and here. So it stands to reason that it must be negative there and there in the 180 minus quadrant and the 180 plus quadrant. Next up, I need to get my reference angle. So RA stands for reference angle. And I do that by kind of taking this cos over, but you never ever use the negative. So if there's a negative here, you never use it in your reference angle. Okay, we're going to slap that in Dr. Uncle Calculator, but okay, he's tuning us a crispy little 60 there. And now that we have the reference angle, we can go ahead and get our general solutions. So let's start off with our quadrant 2 solution. So in quadrant 2, it's 180 minus the reference angle of 60. And then because I'm working with cos, it's got to be plus k360. And k is always an element of integers. So 180 minus 60 gives me 120. And then I'll just slap on that plus k360. K is an element of integers. Okay, let's have a look at quadrant 3. And in quadrant 3, it's just 180 plus the reference angle, and then we just slap on our plus k360. K is an element of integers. 180 plus 60 is 240, and once again plus k360. K is an element of integers. And just by the way, what goes on the left here in the equations is whatever angle you see here glued to the cos. Okay, so that wraps up factor 1. Now we've got to do that same process for factor 2. So we're going to start off by making it equal 0. We're going to take that -1 over, and it becomes +1. Now with general solutions like this, I can actually think of my cos graph to get the answer. So if I have a look at my cos graph, I want to know where my cos graph has a y value of 1. So it has a y value of 1 there, and the theta value is 0. And then I have to go 360 degrees that way to get to my next theta value. That's going to return me a y value of 1, and that's at 360. And then that pattern is going to keep repeating itself. So what I can say is that theta will start on 0 degrees, and then I say plus k360 because every 360 degrees later I'm going to get a 1 as a y value. So that's a bit of a shortcut of doing your quadrants, reference angle, and solutions. It only works with like nice whole numbers like 1, 0, -1. So yeah, keep it brief and short. Only apply the shortcut in those 3 instances. And our 5 marks are awarded in the following places. Isolating cos over there. The k is an element of integers, gets a mark by itself. The 2 general solutions down here get a mark. Isolating cos in factor 2 gets a mark, as well as your general solution for factor 2. Yeah, it's me, I'm back. Alright, we're going to be doing some wild slungs, known as trig functions. So here's a broad overview of the question we're going to do in today's video. So let's go ahead and get started. Okay, so I'll always start by color coding my graphs. This makes a very distinguishable difference between the 2 functions. Now firstly, we need to write down the period of g. G is our blue graph. So what they're essentially asking you is how long is one cycle of your cos graph. So from here to here, it's 180 degrees long because it goes from 0 to 180. So our period is simply just 180 degrees. And there is ways and means of working that out. If you didn't see the cycle, we could just say 360 divided by the number in front of x. That 2 over there, that will return us the period of 180. Next up, we need the range of g of x, which is still our blue graph. So range focuses on y values, and we've got to state the minimum y value that the graph exists at, as well as the maximum y value that it exists at. So we're going to come to our graph and try to find those. So if I look here, this is the lowest point that the graph ever reaches at -1/2. And then if I go to the top, the highest point it ever reaches is 1/2. And that's kind of further being amplified by this half here. That's in front of cos 2x. So we're going to put those guys in. And remember to use square brackets because it does include those points. The graph does exist there. And bear in mind another notation is possible. I can write the y like this and do two inequalities that both point to the left. Take note of how they're inclusive because these are square brackets. And then in a similar fashion, we chuck the maximum on the right and the minimum on the left. And our 3 marks come from the correct period, the correct interval, as well as the correct notation. In the next question, we need to use the graphs to determine graphically the values of x, where f of x, our red graph, is bigger than 0, aka where is it positive? So we're going to have a look at the red graph and look where it's above the x-axis. It's above the x-axis over here in this little region. So to describe our answer, we've got to tell the teacher or the person marking our work, where does this little region start and end? So let's quickly set that up. Now it's got to be x values, the values of x. So we're going to say x is an element of, and we're going to describe where it starts. It starts over here at 45, and take note of how I'm using a square bracket because there's an equal sign over there. So let's chuck that 45 in as our starting value, and now our ending value, we can see it ends here at 90, so we just chuck that in there. Now take note, that is an asymptote. So you've got to put a circular bracket around it because if you look on the graph, that is an asymptote of the tan graph. So you cannot include that 90. Now our questions are going to get a bit more difficult throughout. So in 6.3.2, f of x times g of x must be greater than 0. F of x and g of x are y values. So we're going to be analyzing the y values of the graph. And to give you a clearer picture of that, I've kind of illustrated it with positives and negatives here. So we can kind of see like the tan graph over here that has negative y values because it's underneath the x-axis. As soon as these graphs go above the x-axis, they've got positive y values, as you can see with these green positives over here. So our mission is to find out if I multiply these two y values at the same time, where do I get a positive number? Where do I get something that's bigger than 0? So there's going to be two cases where that happens. Positive times a positive or negative times a negative. So I can see my strategy is I start all the way on the left of the graph. So if you go all the way up the left, I see a negative and a negative at the same time if I kind of draw a vertical line, So it's working over there. So that is a region I can list in my answer that starts at negative 90 and ends at negative 45. And we're going to be using circular brackets because there's no equal sign by this inequality. So let's go ahead and list that first region to be from negative 90 to negative 45 with x is an element in front of that. And then we're going to slap the word or, and we're going to start looking for other intervals. After I cross that point, I've got a positive times a negative, which does not satisfy that. So I move on. So let's see what happens when I cross this point. Now I've got a positive times a negative, so it's still not working. But after I cross this asymptote, hello, little negative times a cheeky little negative, hey, it's working, brah. So, that's going to start at 90, and it's going to end at 135, because after I cross 135, G all of a sudden has positive Y values. So let's go ahead and list that as our answer and finish up with this question. And your 4 marks are awarded for the following parts of your work. In 6.3.3, we need to determine where 2 tan x plus cos 2x equals 2. Okay, that's a bit strange, like where did these come from? So they're playing a bit of smoke and mirror with you. You've got to reorganize this so that you see the equations of the graph. So the first thing I'd want to do to get that accomplished is move this 2 over to that side of the equation, it becomes negative 2, and move that cos over to the other side of the equation. I basically want one of the equations on the left hand side of the equal sign and the other equation on the right hand side of the equal sign. So let's go ahead and make that change quickly. Now 2 tan x minus 2, that's, yes, it's close to this, but not quite. And minus cos 2x, it's also close to this. So how we get rid of this 2 so that we just get a tan of x is we divide every single term by 2, and we're going to get tan x minus 1 equals minus a half cos of 2x. Because if I divide this by 2, there's an imaginary 1 there, so it turns into negative a half. Now look, we have the blue graph, there's his equation. And we have the red graph, there's his equation. So this was all a fancy little ploy to ask you which x values are for the points of intersection. Okay, I see one point of intersection between these two graphs where they touch. Bear in mind, the asymptotes don't form part of the tan graph, they're just a place where the tan graph never touches. They're not actually part of the graph. So, that point of intersection I'm recognizing is over here, and that is located at the x value of 45. And that is literally our answer to this question. X equals 45 is where this mess happens. And your 3 marks will be awarded for the following steps in this question. In 6.4, we've been given a weird trig expression, and we need to describe the vertical translation of h from f. So I so desperately want to simplify this thing, and I have to pull this question off. So there's one term in the denominator, so I want to split up the numerator over the original denominator like so. So I put sin x over cos x plus cos x over cos x. And a sneaky little trig identity emerges, but sin over cos will change into a tan theta, but in our case, it's going to be a tan x. Cos over cos is simply just 1. So now what I like to do is I like to line h of x and f of x next to each other and ask myself, how did I transform f of x into h of x? Now the crucial difference I'm seeing here is negative 1 over here and plus 1 over here. So I'm going to ask myself, how can I change that negative 1 to a plus 1? And I'll simply just do that by adding 2. Now I've got to pay special attention where I added the 2. I added the 2 to the q value, which is like on the outside here, which means it's a translation that went up or down. I know it went up because I added 2. So this plus tells me it went up, and this tells me how much it went up. It went up 2 units. So if I have to describe the vertical translation, it was translated up 2 units. And our 2 marks here come from manipulating this expression into tan x plus 1, as well as our final answer of translated up by 2 units. Wrapping this question up, we need to determine the maximum value of p of x, which is a completely new function that's equal to 4 times g of x. So we know things about g of x. It's our blue graph. And we know the maximum of the blue graph. We got it earlier to be that half over here. So if we want the max of px, we're just going to maintain the structure over here. We're going to say 4 times the max of g of x. So it's just 4 times a half, and that's going to give me 2. Now I really want to take this opportunity to show you what that does graphically. So this new graph I've represented in like a yellowy gold kind of color. What we're doing is taking the maximum of our old graph, timesing that by 4, and we're getting a much more stretched out graph in a vertical sense. It doesn't stretch it out horizontally, only vertically. So you can take note that the blue graph and the gold graph have the same period. They haven't been stretched out at all. But yeah, I'm rambling now. That wraps up this question with our wild snakes, China beans. So all the information they've given us here has been put on the sketch, with the exception of one little piece of information. CB equals 3 times the size of AB. So to conceptualize it, I think about it like this. If AB was the size of x, then CB would be 3 times that size of x. So CB will be 3x. And we're going to go ahead and put that on our sketch. So CB is 3x and AB is just x. Now if we're inside of a 90-degree triangle, we are safe to use SOHCAHTOA. And I'm going to assess my angle. My angle's over here. And relative to that angle, I have the adjacent side of 3x and I have the opposite side of x. So if I have opposite and adjacent, that's going to make me want to choose tan. Okay, now we're just going to modify it to suit our needs. So tan of our angle, so our angle is P, so let's go ahead and change this theta to a P. And our opposite side is x, and our adjacent side is 3x. So let's make those changes here inside of tan. And then once we make that change, we can actually simplify a little bit. These x's will actually end up cancelling, and I can simplify tan P to 1 over 3. And then to get angle P on its own, I'm going to move this tan over. So if I'm breaking tan up from the angle of P, and at the same time moving it over, it becomes shift tan of a third. Okay, we're going to pop that into our calculator because we cannot do that in our head. And we get 18,4349. Just take note of these instructions, correct to 3 decimal places. So if we adhere to those instructions, we are going to get 18,435 degrees. And our 2 marks are awarded for this step over here, as well as our final answer. In 7.2, if P equals 18.4, hey, hello, yes, that's telling me my answer's right, my boy. Alright, so I need to determine the length of CD. CD is over here. So they gave us P, so let's kind of fill P in there and there to get this. I'm going to get 18.4 there, over here. P divided by 2, if I take that P value divided by 2, I get 9.2. So this angle over here is 9.2 degrees. And with that, we need to determine the length of CD. Now CD is inside of a triangle that does not have a 90-degree angle. So we're going to have to use other rules. We can't use SOHCAHTOA now. So we're going to have to use one of these 3 rules. The sine rule, the cos rule, or the area rule. Now they've mentioned nothing of area here. They don't want me to calculate area. They haven't given me area. So we're going to scrap the area rule. So it's between the cos rule and the sine rule. So I'm going to look what I have inside of this triangle. So I've got this side over here. And then I've got 2 angles. So I'm not seeing any one of these cases. I'm not seeing 2 sides in the included angle like this. So if I had like these 2 sides over here and the angle between them, it will force me to use the cos rule. But I'm not seeing that here. I'm seeing 2 angles and a side, so we're going to go ahead and use our sine rule, which we're very happy about because the sine rule is quite easy to use in comparison to the cos rule. Now what's your sine rule? You're never ever going to use all 3 at once. You're just going to use 2 of them at once. So I'm going to scrap the C's. And then I normally start with the thing I'm trying to like find, the thing I'm trying to solve for, the side length I'm trying to get. So I'm trying to get the length of CD. So I'm going to put CD in A's place here. So let's go ahead and make that change. Okay, so now I need to find the angle across from CD. So if I go to CD, the angle across from it is this 9.2. So we change this angle here to 9.2. Okay, now we're going to shift our attention to the second ratio. This has to be a side length that I know. The only other one I know is 121. So I'm going to slot that into B's place here. And then angle B is the angle across from that 121. If I go across from there, it's the 135. So that's going to get filled in over here. And now, once I've filled everything in, my mission is to get CD by itself. So we're just going to cross multiply the sine of 9.2 up to the top over there, like so. And once I do that, I'm just going to get CD equals this mess. And then that mess goes straight on the calculator. There's no way you can work that out in your head. So we're just going to slap that into Dr. Uncle Calculator. Oh, yes, 27,36, bro. And just make sure that you have the correct unit of meters next to your answer. And wrapping this question up, you get 1 mark for your substitution into the sine rule, 1 mark for manipulation, and the last mark for your final answer. Starting off with question 8, we jump into our measurement. We have been given a square-based prism with x, x, and h as our dimensions. And we need to determine the height of the tank in terms of x, and we are going to be utilizing this formula they gave us to do that. The area of the base multiplied by the area of the height. So the base of our square-based prism is the square at the bottom here. And the height of our prism is just this height that goes up and down over here. So we're going to fill the volume in. The volume is 490. So we're going to fill that into volume's place. The area of the base, we just say length times breadth. So it's x times x. So the area of the base is simply x squared. And I'll multiply that by the height. Now if I need to determine the height, it means get the height on its own. So I want to get rid of this x squared. We're going to accomplish that by dividing both sides by x squared. They cancel over here. And I'm left with an expression for my height to be 490 over x squared. And then I'm done. I've successfully answered the question. And your 2 marks are earned from substitution as well as the correct answer. Next up, we need to show that the external surface area of the tank is given by the following complicated formula. So I kind of ignore this formula. We've got to show how they get it, because you see they say show there. So if I look at this tank, they said it's an open tank, so we're not going to consider the top face. So we've only got 5 faces to worry about. We've got to worry about the square at the bottom, this blue oak. And then we've got 4 side rectangles. We've got this rectangle here on the side, this one on the other side, and then we've got the front one, and we've got the back one. Luckily, these 4 rectangles have the exact same dimensions because the bottom is a square. So the length and the breadth of each rectangle is the same, so I can just say 4 times 1 rectangle. Okay, so the area of a square is just length times length. The area of a rectangle is length times breadth. So if we had to formulate our area equation, the area of this blue squared will be x times x, which is just x squared. And then I'm going to say plus 4, because I want 4 rectangles. And then I'm going to do length times breadth of the rectangles. Now for orange rectangle, the length is x, and sort of the breadth is this over here. It's the height, but in the previous question we said that the height is equal to 490 over x squared. So the length of the rectangle is that, and the breadth of the rectangle is that. Now we're going to focus our attention towards simplifying this mess. So the first thing I do to cope with my algebraic fractions here is put this x over 1, and then this x will cancel with one of those x's, and I'm just left with 490 over x now. And then I put this 4 over 1, 4 times 490 will give me that 1960 they have over there, and then I just wrap that in a set of brackets with the centimeters squared on the outside. And now I've successfully shown where this came from. And lastly, wrapping this question up, you get 1 mark for the area of the blue base and 1 mark for the area of your rectangles. In question 8.3, we've been asked to calculate the total external surface area of the tank if we are given that the tank is 10 centimeters high. So what they've actually given us is this h over here. They told us this h is 10 centimeters. So we can put that h in there, we can replace this with 10 and work out x, put it into this area expression, and then it's going to pop out our answer. So let's go ahead and start nitpicking this. Okay, so we're going to make the necessary replacement, swap h for 10, and we get 10 equals 490 over x squared. Now we're going to swap the 10 and the x squared so that we start the process of getting x by itself. So after we make that swap, 490 divided by 10 is simply just 49. Then I need to get rid of the square on x. So the opposite of a square is a square root. So I'm going to square root both sides and I get x to be 7 centimeters. Okay, we're going to come chuck that into this x and this x, just like this. And then that's going to spit out our answer of 329 centimeters squared. Just remember, check with the Dr. Uncle calculator to help you out with that one. You see, it gives me 329, my bro. And our 4 marks come from the following steps: substitution, manipulation, and your answer for x, as well as the total external surface area. Question 9 takes us to the Euclidean geometry within the paper. And we start off with a proof. And we go prove that angle ROQ is equal to 2 times the size of angle P. And we've got to start that off by doing a construction. So we're going to do the following construction. We construct the line PO that's produced. So when I say produced, it means like you draw the line PO and then you carry on drawing it through O. So that's what produced means. You carry on the line. And by making that construction, we're going to form angle P1 and P2, as well as O1 and O2. Next up, we're going to light up P1 and Q. Those two angles are going to be equal because OP is a radii, OQ is a radii, which means they have equal lengths. So we've got an isosceles triangle, and angles op equal radii will be the appropriate reason to use. Yeah. Now from that, we can see that angle P1 or angle O1 over here is 2 times the size of P1 because it's an orange one plus an orange one due to exterior angle of a triangle, and we get O1 over here to be 2 times the size of that orange guy. Okay, now in a similar fashion, we're going to come do that in this triangle down here, OPR. And we're going to say R equals P2. That's because of the angles opposite the equal sides there. OP is a radius. OR is a radius. So we have a very similar thing happening over here. Angles op equal radii. So then O2 will be 2 times the size of P2 over here. And now we kind of have almost done it. You see angle P over here. It's an orange one plus a blue one. And then angle O over here is 2 orange ones plus 2 blue ones. So how are we going to write that up? Firstly, we're going to go through and write a statement that O1 plus O2 is the same thing as 2 times P1 plus 2 times P2. I'm basically replacing this O1 with what I got it to be there. So that slots in O1's place. And I'm replacing this O2 with what I got it to be there. So that gets replaced over there. Then I remove a common factor of 2 from this side. So I'm going to take 2 out. And I get O1 plus O2 equals 2 times P1 plus P2. And that successfully proves what they're asking. To prove that ROQ is 2 times the size of P. So we just jump to that statement. So we just say therefore ROQ equals 2 times the size of P. And our 5 marks, or 6 marks in this case, will be awarded for the following steps: constructions, statement reason, statement, my bre. Okay, jumping off into our juicy Euclidean geometry, we need to find the size of angle D. Angle D is nested over there. And I don't know if you've noticed, but angle D is sitting inside of a bow tie. So to get angle D, we're going to have to apply angles in the same sec, which states that you have equal angles provided they are subtended by the same arc or chord. So applied over here, we've got a little bow tie over there. Can you check him out there, but so D will just be 55 because it's equal to G due to angles in the same sec. Next up, we have to find O2, and O2 is at the center of the circle. So we're going to use our theorem with the center. Angle at center equals 2 times angle at circumference. And it could look like one of 4 things. In our case over here, we're getting like this arrow shape, as we can see if we highlight those. So the angle at the center is going to be 2 times the size of the angle at the circumference. So double the size of 55 will give you 110 degrees for O2. And yeah, there's the size of O2. And this is just your reason. Angle at center equals 2 times the angle at circumference. Next up, we need to get the size of E2. E2 is over here, and what I'm noticing is that it is inside of a triangle we know quite a lot about. We know what this exterior angle is, and we know this opposite interior angle is 90. They kind of told us that earlier in the question by saying DF is perpendicular to EG. So we are simply just going to utilize the exterior angle of a triangle where we add together the opposite angles to get the outside one. We're going to do it in a bit of a backwards order. So 90 plus something must give me 110. Or I can say 110 minus 90 to get E2 to be 20 degrees. And that wraps up E2, my friend. Lastly, we need to get the size of E3. So E3 is sitting over here, and it's touching a very special line. It's touching a sneaky weasel, my friend. It's touching a radius, and there's another radius there. And it forms an isosceles triangle. And E3 is equal to F1, and we've got to use that fancy reason. Angles up equals sides, but... So here's the equal sides. The angles opposite them have to be equal if the sides are equal. We're going to modify this a little bit and say angles op equal radii. And with that, we can actually work out the size of E3. Now I'm going to show you the most efficient way to get that done. So we're going to start by saying E3 equals 180 minus 110, and then we divide that whole thing by 2, and then we know this because of interior angles of a triangle. So basically what we are doing here is we're saying 180 minus this angle of 110, that's going to give us 70, and then we divide that by 2 to split it in 2 equal parts for E3 and F1. So we're going to get E3 to be 35 degrees using that calculation. And now we can see that all the angles add up perfectly to 180 inside of that triangle. And wrapping this question up, let's have a look where the 16 billion marks come from. They are awarded in the following places: pretty stock standard statement reason for the first 3, and then for the last one you get statement reason marks pop over there, and then one for the statement and reason of interior angles of triangle. And the last question from question 9.2.2 asks us to find the length of OH. OH is over here, and I'm noticing it's inside of this triangle. So if I just get the length of one other side of that triangle, I can use SOHCAHTOA because I've got this angle over here. And they've kind of hinted as to which side you must do indirectly with this piece of information. So if I transpose that on the diagram, they've given us this length to be 9.4 units. And I can see one of my circle theorems, line from the center, that is perpendicular to this red chord. And that theorem states that your chord is bisected. It's going to be cut in 2 equal parts, which means this chord over here is chop, chop, cut in 2 equal parts, baba. And just to show you where that 4.7 came from, you just take that 9.4 divided by 2 and you get the 4.7. So that's how we got EH to be 4.7 units. And now, as we mentioned earlier, we are going to use SOHCAHTOA to find the size of OH. Now, if I have a look at this sketch over here, I have the adjacent side there, adjacent to the angle, and I want the opposite side. So I have to choose the trig ratio with adjacent and opposite. So we're going to be using tan in this case. So let's modify it to suit our needs. Tan of our angle is 20, so let's chuck that in the angles place. And then the side that is opposite our angle is the side OH. So we're going to replace opposite with OH. And then our adjacent side is 4.7 long. So we're going to put that into adjacent here. And now we're just going to do a little bit of algebra to get our way out of this and get OH on its own. So I just times both sides by 4,7. And I get OH to be 4.7 times tan of 20. We're going to slap that in our calculator, press equals, and we get this 1,71. So we chuck that there, and then just make sure we have the right units. So they didn't give us units, so we have to write the word units over there. And your 4 marks here will be earned from the statement and reason over there, getting the correct ratio for tan of 20, as well as your final answer of 1.71 units. So we are crossing over to question 10, Euclidean Geometry, but with no numbers, just with x's and weird and wonderful stuff. So we've been given a diagram. We've got angle x here, and first up we need to get 3 other angles equal to x. So first off, I can see x is in an alternating position to another angle over here. So it's the z or the n, which is alternating angles. So from that, I can draw the conclusion that b1 is also x. So I just state that like this, b1 equals x. And let's modify our reason to suit our needs. Our parallel lines here are TV and let's say BC. Once that is out the way, the first angle is always kind of the hardest, and then it kind of flows from there. So now I'm going to go to that angle I just got x to be, and I'm going to try and get another angle equal to this x. So hey, look at what that is sitting inside of. Oh my goodness, it's an isosceles triangle, my bro. So we know angles op equals sides, but we can light up another x down here at V1. And it's the fancy kind of reason for isosceles triangle, or it's one of the properties of an isosceles triangle. The angles across from the equal sides are equal, and you can see we've made that deduction here by concluding that this angle V1 is x. Okay, 2 down, 1 to go. To get this last sneaky little x, we have to use the tan chord theorem. And how we utilize it is we go here and we look for this angle, the angle in between the tangent and the chord, and then we go to either ends of the chord, follow that down, and down some more, and then we get an angle that is equal to this angle between the tangent and chord. So we know that these two angles are equal. So T2 is also x, and our reason is the tan chord theorem. And you get 3 marks for reasons over here, and 3 marks for your statements. In 10.2, they tell us ATVC is a parallelogram, and we need to prove that AT equals BT. So the goal is to prove that AT is equal to BT. The easiest way to do that is to prove that these base angles are the same, which makes this an isosceles triangle, and then we can conclude that AT is equal to BT. So I'm going to direct my focus towards proving these two angles are the same. So I'm going to choose one of them to start off with. I'll start off with A over here, so this angle over here. I'm noticing that that A sits inside of this parallelogram, ATVC. And a certain characteristic of a parallelogram is that your opposite angles in a parallelogram are equal. So if we apply that here, Then this one here is this x plus x, which is 2x. So the whole of angle A will have a size of 2x. So let's see how we write that up. We simply just say A equals 2x op angles of a palm. Okay, now that A is sorted out, I'm going to focus my attention on B3. So if we have a look at B3, I'm noticing something about it. It is sitting outside of a cyclic quad. So if you check this line of the cyclic quad, if I just had to extend that line a little bit like that, B3 actually forms the exterior angle of that cyclic quad. And there's a theorem we have to know about an exterior angle of a cyclic quad. It's equal to the opposite interior angle of the cyclic quad. So if we apply that here, then this interior angle of our cyclic quad is 2x. Applied to the exterior angle, it's going to be equal. So B3 also adopts the size of 2x. And then we just go ahead and state that like this. B3 equals 2x, exterior angle of cyclic quad. Okay. And then once we've proved that both of those are 2x, it's really good to show the link between them. So just do a statement that says that A equals B3 equals 2x. You can put proven as your reason, but it does not really matter. So then after that, if the base angles are equal, we formed an isosceles triangle, and we can conclude that the sides are equal. So we've leapt to our conclusion. AT is the same length as BT. And let's have a look where the marks come from. Stock standard, statement reason, as well as your reason for the final answer. And rounding out question 10, we need to determine the size of x. So a good strategy for this is if you can find a triangle, we can add up all three angles of the triangle to 180 degrees and then solve for x. But we have to look for a triangle that we know all the angles in terms of x. So I can see one in our sketch right about up here, but you see in there, we've got all the angles in terms of x. So this angle plus this angle plus this angle will add up to 180 degrees, but let's form a statement there, brother. So we're simply going to do what we just said. We're going to add up all the angles and they equal 180 due to interior angles of triangle. Okay, 2x plus 1x will give me 5x. Now I need to get rid of this 5. So we're going to divide through both sides by 5 to make that happen. And we get x equals 38 degrees. And after triple checking that with Dr. Uncle, my mental maths has failed me. It's 36 degrees. Sorry for that, bro. And that is why you always triple check with Dr. Uncle calculator, my bro. And just rounding this question out, 2 marks, 1 for statement, 1 for reason. We are entering into our last question of this paper, question 11. We've been given 2 overlapping circles. We've been given a couple of tangents to each of the circles. And we need to start off by completing the following statement. D3 equals something plus something exterior angle of triangle. So let's go have a look at D3 quickly. So what I do with D3 is I recognize the 2 lines that it's touching. And I kind of draw those lines in my head. And then I try and draw up a triangle that joins those 2 lines. So I'm seeing if I draw this line, that's the only real triangle I can make here. I can't really join up another line to connect with this orange line. So we're going to draw this line that connects them and we can see our triangle then. And once we recognize our triangle, we simply just add together the 2 opposite interior triangles. So that's going to be H1 and E1. So we just slot those in here. So it's H1 and E1. Now, don't forget about that. That's going to be very important. I'm actually going to color code H1 and E1 in different colors so that we can conceptualize this question a bit better. And if I do that, we can see that D3 is like an orange angle plus a blue angle. Okay, so taking that in our stride, we need to prove that DFH is a cyclic quadrilateral. And when it comes to proving that something is a cyclic quadrilateral, you've only really got 3 possibilities. You can aim for the bow tie, prove that the opposite angles add up to 180, or you can prove that the exterior angle equals the opposite interior angle. And if we look at our sketch, it's kind of guiding me to this one, because what we just got was the exterior angle of this gray figure that we are trying to prove is a cyclic quadrilateral. So I want to aim for this one, converse exterior angles of cyclic quad. And the best way to go about that is the exterior angle here is a blue one plus an orange one. So we want to prove that this angle down here is a blue one plus an orange one. So let's make that happen. So let's start that process off by utilizing the tan chord theorem. So if I look at the blue angle is nested in between a tangent and a chord. Go to either ends of that chord, follow it down some more, and I get another blue angle down here. So with this information, we can conclude that E1 is equal to F1 for the reason of tan chord theorem. And in a very similar fashion, we're going to come to this orange angle over here, H1. H1 is also nested in between a tangent and a chord. Go to either ends of that chord, follow it down some more, and we find another orange angle down here of F2. So we write it up just like this, H1 equals F2 for the exact same reason, tan chord theorem. Now we've essentially done what we set out to do. We proved that the exterior angle over there is equal to the opposite interior angle over here. We've just got to state it in a mathematical manner. So we have an expression for D3 over here. It's equal to H1 plus E1. Now this angle F over here, I'm going to call it HFE. Angle HFE is comprised of two separate angles. It's comprised of F1 and F2. And we just proved that F1 and F2 are equivalent to E1 and H1. So we can make that switch over there. And now that angle is a blue one plus an orange one. We have D3 is also a blue one plus an orange one. So by virtue of this fact, the whole of angle F equals D3, or HFE equals D3. So we've got to show that link. So we just go ahead, write that up. And then you can include a reason. It's because they both equal E1 plus H1. You don't have to if you don't want to, because no marks get awarded for that. After that, we're going to leap to the conclusion that DEFH is a cyclic quad. And we utilize the converse exterior angle of cyclic quad to prove that. We proved this exterior angle equals opposite interior angle. So due to the converse theorem, DEFH is a cyclic quad. And wrapping up these two questions, we get 1 mark for the correct sort of inputs over here. Statement, reason, statement and reason, as well as your reason of converse exterior angle of cyclic quad. So you could have even left this out. This was me overcomplicating things a little bit. I just wanted to show you it's a little bit more in depth. But yeah, that wraps up this. So on to 11.3. Next, we need to prove that DF bisects the angle HFE. So this line DF, we have to prove that it cuts this angle HFE in half. So we've essentially got to prove that these two angles are the same. So we have to prove that the orange angles are the same as the blue angles in essence. Okay, and Euclidean geometry is normally a story. You normally use your previous answer to help you. Remember, we proved that this gray figure is a cyclic quad. So I can just utilize angles in the same segment. And we just utilize this bow tie over here to show that your blue angle is the same size as the orange angle. Okay, let's write that up. So now I'm going to change them all to orange angles because they're all orange angles, with the exception of D3. D3 is 2 times the size of an orange angle. So to wrap this question up, we're going to trace our steps. So we said that E1 was equal to F1 in the previous question due to the tan chord theorem. So I can put tan chord theorem as my reason, or I can just say proven. and then E1 and E2 are equal, or F1 and F2 are equal to E1. So due to that fact, they must be equal. And then we're going to leap to our conclusion that states that DF is bisected by H. DF bisects the angle HFE, because we just proved that this angle is the same as this angle. So the line DF cuts this angle HFE perfectly in half. Okay, this question is not for the faint of heart. 7 marks. If K1 equals E1, indicated by the orange angles, we've got to prove that GK is a tangent to the larger circle. So to prove that GK is a tangent to the larger circle, I'm going to have to utilize the converse tan chord theorem. In these sort of questions, you have to start with a conclusion to actually know what to do. So with the conclusion that I'm going on about, we identify our chord here, and we follow that chord down some more, find the angle it subtends, and essentially we want to prove that these blue angles are the same to pull this off. So if we prove that those blue angles are the same, E2 and K2, then we can conclude that GK is a tangent to the circle using the converse tan chord theorem. So there's the end of our process. Now we've got to make this happen. We've got to prove that E2 is equal to K2. So to make this happen, I'm firstly going to start with one of the angles. Let's start off with K2. So you see this orange angle and this blue angle. They're both angles of interest. They told us something about K1, and we want to prove that K2 is the same size as E2. So I want to incorporate these two angles, and I'm going to do it using exterior angle of this orange triangle here. Now we can see this exterior angle, K1 and K2, will be equal to this one plus this one, using exterior angle of triangle. So we're going to have K1 plus K2 is equal to F1 plus E2. Okay, they told us, or in the previous question rather, we said that E1 is the same size as F1 due to the tan chord theorem, or I can say proven here since I did it in previous questions. So I'm going to swap this F1 to a E1 now, and we get this expression over here. Now, earlier on in the question, they told us that K1 is equal to E1. So if K1 is equal to E1, and I'm adding the same thing to both of them, then K2 has to be equal to E2. And we just need to state that K1 is equal to E1. That was given to us in the question. And if you want to take a graphical approach, you see how this exterior angle is an orange plus a blue angle. So we've already got an orange angle here, so this has to be a blue angle. And we conclude that by saying that E2 is equal to K2, and then we jump to our conclusion and say that GK is a tangent to the circle KEF due to the converse tan chord theorem. And your 7 marks will be awarded for the following steps. And that wraps up this wild bloody snake of a paper, my China beans.